I want to talk about entrance and exit dosimetry. There's another podcast about this already, but I wanted to give you a little bit more of a clinical example. Again, I have a rando phantom, anthropomorphic phantom. I've overridden the density to be water, so we don't have to deal with any inhomogeneities caused by the vertebral bodies. So for this example, I have a single 6x beam set at 100 centimeter SSD, and my calc point, well anyway, the rando phantom is 20 centimeters thick, anterior to posterior, and the calc point's right midline midplane, so 10 centimeters deep. Now I know that this isn't really a true clinical example because we're not going to use a single 6x beam to treat a calc point that's 10 centimeters deep. It just wouldn't make any sense. But for the illustration of entrance dose and exit dose, I think this is gonna suffice. So I've got my calc point located midline midplane on the central axis. I'm prescribing 200 centigrade to that calc point. I'm normalized at the 100% isodose line, and you can see that my monitor units are 304 that it calculated. We can double check this. So I am 10 centimeters deep to my calc point. We can double check the report printout. Okay, so field 1, 200 centigrade. I'm 100 centimeter SSD and roughly 10 centimeter physical depth. Ignore the equivalent since I'm calc to water phantom. So if I look at my beam data tables, I have a 10 by 10 field size, so my S sub C and S sub P are both going to be 1.0. Okay, I have no wedge, no off axis, no trays. And then if I look at the percent depth dose at 10 centimeters and I go over to a 10 centimeter field size, I'm at 66.4%. So if I pull in mu equals dose divided by, in this case, the only thing I have to worry about is percent depth dose, since S sub C and S sub P are both 1.0, and I'm in a standard SSD of 100, which means no inverse square factor. My monitor units are going to be 200 divided by 0.664. And if I pull the calculator in, 200 divided by 0.664 gives me 301 monitor units. My treatment planning system says 304 divided by 304 gives me an error of 1%. In this particular example, that's fine. We're not going to get lost in the details here. I'm certainly within 1%. Some things to explain this could be, the slight curvature of the phantom surface on either the top or the bottom. Regardless, what I'm left with is a dose distribution that looks something like this. Let me blow this up in the axial plane. So I just put a number of different isodose lines on. You can see here on the left-hand side of the page, I've gone from 300 centigrade down to 60 centigrade. You can see that we essentially have 100 centigrade that goes all the way through the patient regardless. So the two regions that we're interested in are going to be the entrance dose, which we would call Dmax dose, and then the exit dose, which would be Dmax on the opposing side of the body, is typically where we specify the exit dose at. So I've got 200 centigrade that goes right through my calculation point. That makes sense because I'm normalized to the calc point, and then I get these slightly increasing larger percent depth doses, larger body doses going toward the anterior, and that's because of my natural percent depth dose curve. So this is the profile for the curve that's going through this this patient's body. At 10 centimeters deep, I'm at 200. Well, this looks like a normal percent depth dose curve because it is. That's how a single photon field behaves in a water equivalent material. So I have increasing dose toward the anterior surface as I'm moving up to a maximum dose, right around that 302, 303 range. Okay, and then after my 10 centimeter deep, I have fall off. So I have decreasing dose all the way down to the opposite side of the body. So that's what describes what that's the description for how these doses behave within the patient's body. Now, the part that we're interested in is Dmax. So how do we calculate entrance dose? Well, I know that I'm delivering 200 centimeters at 10 centimeter depth. I'm delivering 200 centimeters at 10 centimeters depth. 200 centigrade, at 10 centimeters depth. Well, how do we define PDD? Well, percent depth dose is dose at depth right, divided by dose at D max. Okay, so how do we solve for dose at D max? Well, we multiply dose at D max over to the PDD and we divide by PDD, so we get dose at D max equals dose at depth divided by the PDD. Okay, what's my dose at depth? Well, my dose at depth is the prescription dose, right? Because at 10 centimeter depth, I'm prescribing 200 centigray. What's my percent depth dose? Well, my percent depth dose that I looked up in my beam data table was 0.664. We go to 10 centimeter field size down to a 10 centimeter depth is 66.4%. So my dose at D max is 200 centigray divided by 0.664. Okay, 301. So if I looked at my profile again on the central axis, and I look at my D max, right, my maximum dose is 302. So 302 centigray, 301 centigray, effectively the same. So that's my dose at D max. You take the dose at depth divided by whatever the percent depth dose is at that position. Now, exit dose is a little bit more complicated. Well, it can be a little bit more complicated. We can do it two ways. Okay, so I know that my I need to know percent depth dose at that exit point. So if I have a 20 centimeter thick phantom, okay, D max on the posterior side is 1.5 centimeters from posterior edge of the body. Well, 20 minus 1.5 is 18.5. So I'm interested in the percent depth dose at 18.5 centimeters. So if I pull in my data table, 10 centimeter field size, and I go down to 18, I don't have 18.5, so I have to do a little interpolation. Okay, so I have 18 and 19. Maybe your physicist has a 5 millimeter resolution on his data tables. Regardless, since I'm halfway in between 18 and 19, I can just take the average of these two. So 42.7 plus 40.3 divided by 2 puts me at 41.5. So my percent depth dose is 41.5. Okay, PDD at 18.5 centimeters, or the exit, equals 41.5%. Okay. Well, how do we figure out dose at depth? Remember, PDD equals dose at depth divided by dose at D max. Well, all I have to do is multiply dose at D max times my PDD to get dose at depth. So dose at depth is PDD times dose at D max. Well, we just figured out what dose at D max was. I know what my percent depth dose is, 41.5. My dose at D max was 301. Okay, so I have 0.415 times 301 centigray is 125 centigray. Okay. I'll use my ruler to measure 18.5 from the central axis down through the calc point. Okay, and then I can use my dose point tool here, and you can see I have 126 centigray. Okay. So I'm less than 1% different from calculated. So that's going to be dose at the exit. You have to know what the percent depth dose is. So you can do it a two-step method where you can take your Dmax dose times whatever your PDD is at the exit point. Otherwise, the second method that you can do is just a single step method. You know what your prescribed dose is at 10 centimeters deep. So I know the dose at 10 centimeters, so my dose at depth is 200 centigrade. That's my prescription. The PDD at 10 centimeters, we looked that up, 0.664. Okay, I need to know what the dose at the exit point is. I don't know, but I do know that my PDD at 18.5 cm is 0.415. So what we can say is, you can say dose at 18.5 equals dose at 10 centimeters times PDD at 18.5 divided by PDD at 10. So this is a ratio. So that's all this is. So I know my doses, that's all I'm doing here is just a ratio. Maybe I'm skipping a step here where I'm multiplying the PDD at 18.5 over to the other side of the equation. But anyways, it's just a ratio that we're setting up because we know what the two doses are. We know what we know what one of the doses are. We know what the 2% depth doses are. Now we're just doing a simple ratio here to calculate it. So this is the second way of doing it that's maybe slightly easier than the two-step method. So 18.5 centimeters is going to be my exit. Dose at 10 centimeters is 200 centigrade. My PDD at 18.5 was 0.415. My PDD at 10 is 0.664. Pull my calculator in. 200 divided by 200 times 0.415 divided by 0.664 gives me 125. So the exact same answer. So that's the second way of calculating dose at the exit point. It's the one-step method, which I think is shown in the other podcast, instead of the two-step method where you find dose at Dmax and then you apply a percent depth dose to take you to dose down at the exit point. This can be useful for single SSD fields for calculating entrance dose. If you want to find out what your Dmax, maximum dose is within the body. Otherwise, your exit dose, maybe if you have spinal cord or something like that that you're worried about. Okay, that is it.